Well, we're back here with our fifth video in our series of videos talking about polynomial functions, polynomials and polynomial functions. And let's take a look at some different shapes that graphs may have for small degree polynomials. So first of all, we'll start with the simplest ones. Degree 0 polynomials are constant functions. And of course, these are real boring. They're all just horizontal lines. You see maybe 4 of them graphed here, and they're all just vertical translations of y equals 0. They have no extrema, no inflection points, no roots, unless it happens to be y equals 0, and then they're all roots. Okay, so that is a polynomial function. The next simplest kind are the degree 1 polynomial functions, which are linear functions. The graphs are straight lines. All are transformations of y equals x. So here's several to graph. Of course, if the arrow is pointing down on the right, that's with the negative coefficient, negative leading coefficient, which in this case is our slope, m. And if their arrow is pointing up on the right, they have positive slopes, a positive leading coefficient. And they're either all increasing or all decreasing for a particular line. So it's completely straight, so no concavity, no inflection point, no extrema. They all basically look the same. Degree 2 quadratics, they all pretty much look the same as well. Y equals ax squared plus bx plus c. They all have the shape of a parabola. They're all transformations of y equals x squared. There's no change in concavity, so no inflection points. And they have up to 2 real roots. It's either all concave up when a is positive or all concave down when a is negative. If a is positive, concave up, then that vertex is going to be the local and global minimum, whereas if a is negative, it's upside down, and there'll be a positive, there'll be a maximal, okay, global maximum. Now notice that these can cross the x-axis up to 2 times, but you could actually have it where it crosses once or not at all as well. So for example, this one right here, just y equals x squared, for example, has a root of multiplicity 2, where it touches once only, and then turns around. So the graph is it actually touches the x-axis and then turns around there. That's a multiplicity 2 root. The x-axis is actually what we call tangent to the graph at that point. And I don't have one graphed here, but you could certainly have one that misses the x-axis altogether. So you could have 1, 2, or 3 real roots. Now things start to get a little bit more interesting now when we go to cubic functions, y equals ax cubed plus bx squared plus cx plus d. These are not all transformations of a power function. They all have exactly one inflection point, and in some cases, like the transformed x cubed right here, this red one, that inflection point is also kind of has a horizontal tangent line there, and so it changes from concave down to concave up. That's a root of multiplicity 3. Then this purple one, this kind of long skinny one, has an inflection point also, but it's not just a transformation of y equals x cubed, but it does have a inflection point, but no max or min. The purple one here is all decreasing, the red one's all increasing. Notice the arrows on the end will both go in opposite directions, so one's pointing up, one's pointing down. The ones that point up on the right, this aqua one and this red one, have a leading coefficient that's positive. And if the arrow points down on the right, the maroon one, the purple one, and the green one, those have a leading coefficient that's negative. But you could also have, this green one's also like a transformed y equals x cubed. But you could also have these other situations where you could have 2 extrema, and you could have up to 3 real roots. But notice the range is all reals, so you have to have at least one place where it crosses the x-axis. Now that might be it, like in the case of the purple one here and the red one, but it could cross up to 3 times, like this one here. It could actually just cross twice, one of them being a root of multiplicity 2, like the aqua one here. So in a way that sort of counts twice, but it's still just one root with multiplicity 2. So we have that. And we could actually write out some of these, like if this crosses at negative 10 and this at negative 7, this is x plus 10 squared times x plus 7 times some positive number, constant. This red one's just x cubed, x minus 5 cubed. And you could actually have it cross the graph, the x-axis up to 3 times. So this one here is x minus 10, x minus 11, x minus 12 times some negative number. So how much could you have? You could have up to 3 roots, up to 2 extrema, and up to 3 x-intercepts. In fact, you have to have 1, 2, or 3 x-intercepts. It's not possible to get 0 or to have more than 3. You're definitely going to have one inflection point. It'll happen between the max and min if the max and min are there, but it will have an inflection point even if it doesn't have a max and min. If it does have a maximum, it has a minimum. It has one of each. So it either has 2 extrema or no extrema. Alright, things get a little bit more interesting. You can actually look at this here. Another way to look at this cubic one. The closer these max and min get to each other, the closer they are to the inflection point, and the more it starts to look like this, say this x cubed thing here. And if they ever land on top of each other, then you lose the max and min, and you get the inflection point still. So you kind of think of that as a degenerate version. Okay. So here's some degree 4 things, and there are several things that could happen. Sort of the most general, the sort of typical case you want to think about is this green one here, where it comes down, and when you factor this, it has 4 factors that are all different, and they're x minus some real number, and so we get 4 roots, 4 distinct roots. And if you do that, in between the roots, you're going to get a max or a min, and you'll get 2 of one and 1 of the other, so 2 mins and a max, or 2 maxes and a min. And so you get 3 extrema. Between the extrema, you get inflection points, so you have 2 inflection points. So what do you have? 4 roots, 3 extrema, 2 inflection points. Now, there are all kinds of things that can happen here to sort of degenerate. So instead of 4 different roots, you could have basically the same kind of shape here, but you only end up with 3 distinct roots here. 2 multiplicity 1 roots and a multiplicity 2 root. That's possible. You could have 2 roots. Take this one and just shift it up. If this was the axis right here, it could just touch twice. You could have 2 multiplicity 2 roots. You could have just 1 root, like y equals x to the 4th has 1 root of multiplicity 4. You could also have sort of degenerate cases where you don't have the 3 extrema. So there's your 3 extrema. Over here's 3 extrema. But in some of these cases, like this purple one, the green one, this kind of olive one over here, all of those, you sort of had a place where these sort of, if you want to think about it, is sort of the limit of what happens is as these max and min kind of come together and merge with that inflection point, you keep an inflection point there. And so notice we've got 2 inflection points in this thing still, but only 1 extreme value. Here, they all merge together, and then there's only 1 extreme value. So this is probably just a transformation of y equals x to the 4th. Here's another one. It's not just a y equals x to the 4th transform, but actually this one's a little more subtle to see. It's kind of hard to see right here. But if you look, this is concave up, and then somewhere in here there's an inflection point where it goes concave down, and then it goes concave back up again. Hello. Okay, great. Okay, so, okay, well, I'll have to try to have some dinner around 6-ish for you. That's good. I was looking forward to seeing you. Okay. Okay, grab a couple. Come back. So anyway, yeah, this blue one here has an inflection point in here and someone up here. So It goes concave up, then concave down a little bit, concave up. But it's still, I think, but it's doesn't have it has this one minimum. Notice though that the arrows on the end are going to go the same way. So these that are pointing up on the right side are pointing up on the left side as well. Those have a positive coefficient for the leading coefficient. So both of these two here, this blue one, this red one over here, but this purple, this red one, and this green one, those are all pointing down on the right side, so they have a leading coefficient that's negative, and they're also pointing down on the other side. Now if you think about that, because these are going down forever, they have to have a highest point period. So these will not have range all reals. So in the odd cases, the range was all reals, whether that was a line, a linear function, right, non-constant linear function, or whether that was degree 3. But when you have an even degree, like the parabolas in degree 2, they have an absolute extremum, okay, a global extremum. So either an absolute maximum there or an absolute minimum, global minimum or max. Well, these are also going to have a global min or max. Might be a tie like this one for a minimum. Here's a max, there's a max, max, minimum, minimum, minimum on this one. So the range, for example, this one is whatever this y value is on this minimum up forever. Okay, even more possibilities when we go to degree 5. They can have 1, 2, 3, 4, or 5 x-intercepts. They got to have at least one because they take on all reals. And we get a lot of interesting looking shapes here. So the most typical thing you want to kind of think about as your basic example is the red one over here on the left, where we have 1, 2, 3, 4, 5 roots, so that's 5 distinct factors. In between we have max and min, so we have 2 max, 2 min. And we have in between the extrema we have inflection points, so we have 1, 2, 3 inflection points. So 5 roots, 4 extrema, 3 inflection points. But you can see some degenerated cases here, all kinds of weird things that could happen. So you can get this one happening here where we've still got 1, 2, 3 inflection points but no max at all or minimum. This one has 1, 2 inflection points and let's see, concave up and down, that's 1 inflection point, then up again and then down again. So 1, 2, 3 inflection points still, but 1 maximum and 1 minimum locally. No global extreme on this at all. Okay, the number of roots can be different. You can have 5 different roots like this one. Here this one has 1, 2, 3, 4, and 5. The 5th one is that one, the same one again. So 4 different roots. One of them was multiplicity 2. Here's one has a multiplicity 2 root here, I think, or maybe a multiplicity 4 root. This either has a multiplicity 4 root at 0 and then a multiplicity 1 root here, or it has a multiplicity 2 root here and multiplicity 1 root here, and then it has 2 roots that are not real. This one only has 1 root here that's multiplicity 1, so it has 2 pair of non-real roots. It could even degenerate down to something like this, which just has 1 inflection point, or this one, which is just kind of like x to the 5th. So, as you see, the bigger the power, the more complicated things can get, but it can only get so complicated, and eventually it has to settle down by the end behavior. So every time the degree increases by 1, the graphs have the potential to become more complicated, but they don't have to be. I mean, x to the 17th power is really not any more complicated than x to the 3rd power. Okay, y equals x to the 17th, y equals x to the 3rd, they look pretty much the same. But in general, a 17th degree polynomial could have a lot more interesting stuff going on than, say, a 3rd degree polynomial. So every time 1 is added to the degree, there's a potential to add 1 more x-intercept, 1 more extremum, 1 more inflection point. So let's look at some summary of the possible number of things that you have. If it's degree 0, then for sure it is a situation where we have there we go. Try to fix that. Sorry. If it's degree 0, we have a horizontal line. So they're all tied for being maxima minima. So sort of infinitely many max and mins. No roots at all, unless it happens to be y equals 0, and then they're all roots. And no inflection points. That one's kind of a weird one by itself. When you got degree 1, that's linear. It has one distinct real root, no extreme at all, and no inflection points. When you get to degree 2, you have 2 or less on the distinct real roots, or x-intercepts. It could cross the x-axis 0, 1, or 2 times. It must have exactly one local extrema at the vertex there, and absolutely no inflection points. Now when we get to degree 3, we have a few more options here. You could have 3 or less, 1, 2, or 3, but not 0, real roots. And you have 2 or less, well, really either 0 or 2 extrema, and 1 inflection point. If you have degree 4, it's 4 or less, 0, 1, 2, 3, or 4 possible different roots or x-intercepts. And 3 or less, really it's either just 1 or 3 extrema. And the 2 or less inflection points, actually it's either 0 or 2. Degree 5, 5 or less real roots, but it can't be 0. It's got to have at least 1, being an odd power. So 1, 2, 3, 4, 5 real roots, distinct real roots. 4 or less extrema, actually, the extremas kind of go up and down in pairs, so it's either 0, 2, or 4. And one less than that, 3 or less inflection points, and they kind of go up or down in pairs as well, either 1 or 3. It's got to have at least 1. So you can kind of, if we sort of see this, is for the n's that are bigger than 2 at least, there's always n. Remember, n is the degree of the polynomial function. So if n is greater than 2, there's n or less roots. If it's odd, there's got to be at least 1. If it's even, it could be anywhere from 0 up to n. There are n or n minus 1 or less extrema, and n minus 2 or less. Probably should say fewer. N minus 1 or fewer extrema, and n minus 2 or fewer inflection points. Should use the word fewer when you're talking about a discrete situation, and less if you're talking about continuous situations. So if we specify an n, the graph can only get so complicated. So for example, if we say the degree is 8, we know it could go up and down a while. Eventually it's got to settle down on the ends, and we know that the most things it could have is n equals 8 extreme or x-intercepts, at most n minus 1 or 7 extrema, and at most n minus 2, which is 6 inflection points. And I'm going to call all these things critical points for now. And so it could have fewer critical points than that, but that's the most. So you can only get so complicated. On the other hand, if you look at it from the other direction, if the graph has a certain degree of complexity to it, that forces the degree to be a certain, at least a certain size. For example, if you see 3 inflection points, you know that polynomial must have a degree at least 2 higher, degree 5. It might have a degree a lot higher than 5, but it's got to have a degree at least 5. Because you can't do 3 inflection points with anything with a smaller degree than 5. So let's take another graph, say it has 6 local extrema. Well, it must have degree at least 1 more than that of 7. So if it's got 6 local extrema, it has to be at least degree 7. Could be higher, but it can't be less than that. So let's see if we can answer these questions now. What's the minimum degree of a polynomial with 8 inflection points? Well, it's got to be 2 higher than the inflection points, so it's got to be at least 10. What's the minimum degree of a polynomial with 6 extrema? At least 1 higher. Got to be at least degree 7. What's the minimum degree of a polynomial with 9 x-intercepts? Well, basically 1 x-intercept for each root, which means each factor. Roots and factors go together, so you got to have at least degree 9. Could be bigger than these numbers, but it can't be smaller. So this is the minimum amount. So if you know the polynomial is degree 15, how many times could it cross the x-intercept? Well, if it's odd, it's got to cross at least once, but at no more than how much? Well, 15. If it crossed more than 15, it'd have more factors, more linear factors than 15, which would push the degree up higher. What's the maximum number of extrema, local extrema? Well, one less than that, up to 14. Could be fewer, but up to 14. And the maximum number of inflection points? Well, one less than that, 13. Are we guaranteed at least 1 x-intercept? Yes, because it's an odd power. If it had been an even power, no, not necessarily. How many y-intercepts does it have? All polynomials have exactly 1 y-intercept. All functions have either 1 or 0 y-intercepts, but remember the domain of polynomials is all reals, so in fact it always has 1 y-intercept. Exactly. This says we're going to start another video, but we're not. We're going to keep going. Okay. So, next we're going to look at multiplicities of roots and the shape of the graph near the x-intercepts. So you can look at the graph of a function near the x-intercept, the real root, and tell something about the possible multiplicities of the root. If the graph does not actually pass through the other side of the axis, but simply touches the axis and turns around, so the axis is tangent to the graph, and we have a local extremum there, then that's like the behavior of an even power function near the origin, and the polynomial has an even multiplicity root there, 2, 4, 6, 8, whatever. So it has multiplicity at least 2. If instead the graph actually passes through the axis to the other side, it's an odd multiplicity root, so it could be a simple root, multiplicity 1, or not. But if we zoom in closer and we see that it kind of looks like a non-horizontal straight line through the axis there, then that's a simple root or multiplicity 1. But if instead the graph passes through to the other side, but first it flattens out nearly horizontal, so it has a horizontal tangent line of the x-axis, and that root is also an inflection point, then that's an odd multiplicity, but it's at least 3 or more. Remember how the odd degree power functions look like near the origin. So we can see all of that in the graph of this one here. So notice this x plus 8, that says at negative 8 is a root. The power is 1, so that's the multiplicity. The multiplicity is the power here. X plus 2 says negative 2 for x is a root, but the power is 3, so that's multiplicity 3. And x minus 7 says 7 is a root, and the multiplicity is 2. And let's look at the graph, and you can see that what I'm talking about on the picture here. So over here at negative 8, we have multiplicity 1 root. So if you look in right here, it's going straight through, and it's a simple root, or a multiplicity 1 root. Non-repeated. Now this one, we have x plus 2 cubed, so we see a multiplicity 3 root at negative 2, and if you look in here close, it looks like an x cubed here close by. It's an inflection point, horizontal tangent, and goes through there. Over here at 7, it bounces sort of. It sort of hits and turns around, and so there's a local minimum and a horizontal tangent line of the x-axis right there at the root. So that's a multiplicity 2 root. Now, a multiplicity 4 root or 6 root or 8 root would look very similar to this multiplicity 2 root. It could either come down and hit and go up, or it could come from below, hit, and go down. Okay? But it would look basically the same for any multiplicity, even multiplicity root. An odd multiplicity root greater than 1, so a multiplicity 3, 5, 7, 59, they are all going to look very similar to this here. And a multiplicity 1 root, if you zoom in close, is going to look like a line through there, non-horizontal line. Now, we have some basic definitions. Some of these things we've used before. A monic polynomial is a polynomial with 1 as its leading coefficient. A linear polynomial is a degree 1 polynomial. A quadratic polynomial is degree 2. A cubic polynomial is degree 3. A quartic polynomial is degree 4. Quintic polynomial is degree 5, and so forth. Usually, before too long, we just say how many terms it has. A minimal polynomial is a polynomial with smallest degree with the specified characteristics that we say. Now, we have some theorems about polynomial functions. And this one's, with the remainder when dividing p of x by x minus r is p of r. Let's see if we can understand that. So if I take a polynomial and I divide it out, and I can use synthetic division. Let's say I do x minus 3, and we're going to divide that into 2x squared minus 3x plus 4, minus 4, let's say. So I'm going to use synthetic division here. Bring down the 2. 2 times 3 is 6. 3 times 3 is 9. Plus this is 5. So this says that this equals 2x plus 3 plus 5 over x minus 3. Or in other words, if you were to check this, and this is the key right here, you would take the x minus 3, the divisor here, multiply by the quotient, 2x plus 3, and we would add 5. Well, notice what happens if and so this is, so if f of x is my original 2x squared minus 3x minus 4, this should be equal to what we started here. So we could write f of x this way. Well, what happens if I put in 3? The same number that I have right there on my synthetic division. The thing that makes this, well, this expression would be undefined here, but this polynomial would be defined. And if you put it in here, look what happens. This part is 0, so it really doesn't matter what this is. What do we get? We get this number here. So notice that f of 3 is the remainder, 5. So one way we can do this, so watch, you can take this and do 2 times 3 squared minus 3 times 3 minus 4. That's f of 3. 2 times 9 minus 9 minus 4 is minus 13. 18 minus 13 is 5. So that's one way to get it. That's the normal way to get it, f of 3. But we can also take it, do the synthetic division, and whatever that remainder is, that's also the same thing. Now, this can be useful, particularly when that remainder is 0. So if we've got f of x equals, I'll just do a simple one. Well, let's do x cubed minus 27. Okay? What if we do synthetic division and do 3? So 0, 0, 0, 1, 0, 0, 27. Let's try 3. 1, 3, 3, 9, 9. This is negative 27. 27, 0. So we got a remainder of 0. So that says that f of 3 is 0, which of course we can do here, right? 3 cubed minus 27 surely is 0. But not only does it tell you f of 3 is 0, it tells you what the other factor is. So this tells us that f of x actually factors as x cubed minus 27. That factors as one of the factors is x minus 3, the x minus this guy. But it tells us that this is the other factor. We sometimes call this the depressed polynomial. Now, if we wanted to factor, this one doesn't factor any farther on the with integer coefficients, but we could use the quadratic formula on that to find the other factors, even if they happen to not be real numbers. Okay? Alright, so let's take a look at, back to our notes. So, it turns out the following are the same thing. To say r is a root of p of x, or r is a 0 p of x minus r is a factor of p of x, p of r equals 0, and the remainder when dividing p of x by x minus r is 0. So those are all equivalent. Now we got a couple of extra, that's called the factor remainder theorems there. We have called the complex conjugate theorem. If p of x has real coefficients, then any non-real complex roots, if any, must come in pairs, which are complex conjugates of each other. So that means, of course, that if you have real coefficients, if a plus bi is a root, then a minus bi is also a root, which means x minus a plus bi is a factor, and the other factor is x plus, or x minus, still x minus, but a minus bi. There we go. And so these together make a quadratic factor that is, or second degree polynomial factor that is, that's going to be real coefficients. So non-real roots come in pairs if you start with real number coefficients. Now, if I allow non-real coefficients, then all bets are off on that. You could have all kinds of stuff. But if we have real coefficients, any non-real things have to come in pairs. And in fact, it's also true if you have rational coefficients, the irrational ones have to come in pairs as well. Where do they come from? Well, basically, you can always factor this down. If you have integer coefficients, you can always factor it down into linear factors and quadratic factors. And the quadratic factors, then, you can factor them with the quadratic formula. In fact, we can always factor everything all the way down to linear factors. Okay, in fact, a bunch of monic linear factors, as long as the roots are allowed to be complex number system. And this works whether you start with complex coefficients, real coefficients, whatever. Okay, so you have your leading coefficient right here, and then you might have a bunch of factors, x minus root 1 to some power multiplicity 1, x minus root 2 to some power multiplicity 2, and so forth. And so you have k distinct roots, and if you add up all these multiplicities, that's what this sigma thing means over here in the end, you add up the multiplicities, it's the same as the degree of the polynomial. So the fundamental theorem of algebra is a really powerful thing. It says that every single polynomial is going to factor all the way down to linear factors. And so there is no such thing as a prime factor that's bigger than a prime polynomial that's bigger than a linear factor if you're talking about allowing complex coefficients. Now, some things won't factor if you only allow real coefficients. So let's look at let's apply some of this to finding an equation. So let's suppose we have here some table of roots and multiplicities. So the roots are -5, 0, 1, and 3, and you see the multiplicities there. And we want to find a minimal polynomial with the following roots. Well, it's some coefficient a, which could be anything, any real number, and then you've got x minus a -5, or in other words, x plus 5 to the first power, x minus 0 to the second power, x minus 1 to the third power, x minus 3 to the first power. Now we can drop the power 1s and make that invisible. X minus 0 is x, and I'm going to move it to the front. So we would write it as ax squared times x plus 5 times x minus 1 cubed times x minus 3. Now any a will satisfy the conditions we have, and if we and notice that a turns out to be that leading coefficient. Now if you put any a in there, it's just going to stretch and compress this thing, but not change its x-intercept. So the stretching will be vertical. Okay? It's not going to change the x-intercepts. It's not going to change the basic shape of the graph near that. It might flip it upside down if a is negative, but or it might be the other way around when a is positive. But basically just makes it shorter, taller, possibly flipped. Now, how could I know which one it is? Well, if I know one other piece of information, like if I just know, like if I know the y-intercept, or if I know any other point on the graph besides these that are on the x-axis, then I can plug in an x and y and solve for the missing a. So, for example, if we know p of 2 is 3 for this particular function, I can hit this everywhere there's an x, put in 2, which you see I've done right here. And where there's a y, or p of x, I put 3. And then I simply work this out. 2 squared is 4, 2 plus 5 is 7, 2 minus 1 is 1 to the third power is 1, 2 minus 3 is negative 1, 4 times 7 times 1 times negative 1 is negative 28. Divide both sides by negative 28, we get a is negative 3/28. So now we have our very specific polynomial narrowed down. So we can also, we could graph it, particularly if we've got technology to help us. We can graph it on Graphmatica or on our calculator, and we can use that to make tables, either by hand or with a calculator. Answer all kinds of things. So we're going to actually graph it, and this is going to be one graph, but we're going to have 3 different views. And it turns out that it takes 3 views to see this. So this view is sort of the big picture view. So we're sort of way back looking at the function from a distance. And notice we can see the basic end behavior. Notice that it's if we multiply this all out, I'm not going to multiply it all out. It's better to see it in factor form. But if we just did the first term, here we get an x. Notice we get 1 plus 3 is 4. Another one's 5. 2 more, 7. So we get negative 3/28 times x to the 7th plus a bunch of other terms. So it's going to look like an x to the 7th, but negative coefficient on the end. So that should be a down arrow on the right, up arrow on the left. So here we've zoomed out far enough we can kind of see what the end behavior is going to do. And we can get a pretty good picture of this local minimum here between negative 4 and negative 4.5. Okay, so we can see that minimum. But it's way down there, negative 1400 something. But we've lost a lot of detail right in here between, say, negative 1 and 3. It's hard to tell exactly what's going on there. It looks like there might be a maximum right in here, but we really can't tell anything about what's happening in here. So we need to zoom in to see that. Well, we zoom in, we lose some information. For example, now we've got a whole chunk of this where it came down and turned around. Okay. Okay. And we see it turning around here. Well, on this next graph, we can't see it turning around. It has a big gap here, but we know it goes down in somewhere way down there and turns around. But as we zoom in closer, we can see, we can still see the root here. We can still see a root here. Multiplicity 1 roots, you can tell. We can see the maximum here. We can see an inflection point right in here. But we're still losing some detail right in here. So we zoom in a third time. We're in here close. Now we've really lost some information because now we can no longer see this stuff over here at negative 5. We've lost the inflection point that was in there. There was an inflection point right in here somewhere that you can see here. Okay, which we've lost. We lost that on this picture. But now we can see that multiplicity 2 root at the origin like we expect, and the multiplicity 3 root over here at 1 like we expect that shape to be. And in between there's a minimum here. There's an inflection point here and here. Of course that one at 1 is an inflection point. So it may be that you can't really see everything with one picture. It's sort of like looking at a mountain. We can look at it from a distance and we get a real good idea of the overall majesty of the mountain and the overall shape. But we don't know the details. We get up closer, we can see one mountain pretty well, but we still can't see all the details, but we also lost some of the big picture. We can't see the mountain range as well. We get on the mountain, we can see rocks on the mountain and really tell detail, but we've lost the shape of the mountain as well as the mountain range. Now sometimes you can get lucky enough that there's one single window that sort of shows all the interesting things. Now, you never have one window that will show everything because it goes on forever left and right, but you can sort of see with one window all the really interesting part. Sometimes people call that a complete graph. It's not really complete because it does, you're only going to see part of it, but it might be complete in the sense that you can see visually all the interesting stuff. So suppose this is a complete graph. Well, it couldn't be here. There we go. That's our complete graph. And so now we can, suppose we can see all the interesting stuff here. So in other words, what we're saying is, it's far enough back that we can see the end behavior. It is, so it's just sort of same old once it's off the screen. So from here on out to the right, it's still decreasing concave down. From here on out to the left, it's still increasing concave down. This arrow points down, this arrow points down. Okay, we know that's the end behavior. Also, all the maximum and minimum points you can see, all the inflection points are visible as well as the x and y intercepts. So all the interesting stuff is sort of visible in the same picture. So we're lucky there. Okay, well, what's the equation of this guy here? Well, let's see. It looks like we have a simple root here at x equals 1. So that's x minus 1 is a factor. Looks like we have a multiplicity, odd multiplicity root here at x equals 6. So x minus 6 is a factor to the power 3 or 5 or 7, something like that. Probably the third power. And this one here is a maximum at negative 5. So that's and it actually touches the axis there. So negative 5 is a multiplicity 2 root or even multiplicity root. So you have an x plus 5, say, squared, or a fourth power, something like that. We can also see a y-intercept. So let's see if we can maybe come up with a formula for this guy. Okay, so we know it's even degree because the arrows are pointing the same way on the end, and we know that leading coefficient is negative. Okay. So we can look at the maximum. It has a max. Let's see, count the max and mins. There are 3 of those, so that tells us the degree is at least 4. Let's count the inflection points. There's 1, 2, 3, 4 of those. So we're at least, let's see, we'll count those again. 1, 2, 3, 4 that I can see. So there's at least degree 6 for this. Let's count the roots. That's at least multiplicity 3. 1 there, at least 2. So 3 roots, but counting multiplicities, there's 2 and 1 and 3. That adds up to at least 6. So it looks like we're the smallest we could hope for is a multiplicity as a polynomial of degree 6. So those are the roots and the multiplicities that we said. Now let's so put all this together. It's n is even and at least 6. So let's write out a possible formula. Let's see if we can make one with degree 6. So it has some leading coefficient a, which by the way we know is negative because they are on the right pointed down. And then we have x plus 5 to the second, x minus 1 to the first, x minus 6 to the third. Now how can we find a? Well, notice that the y-intercept is 0, 4. See that back on the graph? Right there, 0, negative 4. And then so that means I can plug in 0 for x and negative 4 for y. And you can see I've solved it here. This is 25 times negative 1 times negative, whatever 6 cubed is. Multiply that out, you get 5,400. Divide that and simplify, you get negative 1 over 1350. And so here is an equation that could work. And in fact, that is actually what it is. There are some things that could have been different. For example, this might have been a power 4 instead of 2. This might have been a power 5 instead of 3. But it turns out that the smallest powers possible actually worked. And of course, if those powers had changed, so would the a. Notice the a is negative as we predicted, and we can see this. Now, once you have this graphed, you can approximate roots and extrema. Of course, we know the roots, but the extremum here, of course, that one there's exactly a maximum at negative 5. We know one inflection point for sure is at 6. There's a minimum here, a maximum here. We could approximate those once we get it in our calculator. we could calc do calc, which is second trace, and choose 0 if you want to find the 0 or root. We want on the 82 it says root, on the 83 and 84 it says 0. Minimum or maximum, you can do those. So say we want to count, do the maximum. So if you have a TI-82, when you do a calc max or min, it'll ask you for a lower bound and an upper bound. On a TI-83 or TI-84, it calls that a left bound or right bound, which is probably better because it's to the left and right side. And yes, we've done this before. And so you find out, of course, we know this local maximum at this root because it was a multiplicity 2 root, and we can get this local and global maximum approximated and approximate that minimum there. So here's another exercise. You can try this one on your own. It's very similar to the last one. I think I'm just going to keep rolling here. General characteristics of all polynomial functions. Let's summarize. All polynomial functions have the entire set of real numbers as their domain. They're defined for all real numbers. They're continuous, one connected piece. Differentiable, so they're smooth. They don't have any asymptotes. They don't have any vertical or horizontal asymptotes. They don't have any sharp corners. They don't have any holes in the graph. They're locally linear, so if you zoom in close on them at any point, they look like a straight line. And they often have extrema and inflection points as well as x and y intercepts. Not guaranteed, depends on the function, but they could have some of those ups and downs. They always have exactly one y-intercept, so the same as the constant term of the polynomial is the y-coordinate of the y-intercept. They can have several x-intercepts. The number of x-intercepts can go up to the degree of the polynomial. The x-intercepts correspond to real roots, which correspond to the linear factors of the polynomial. The multiplicities of the real roots affect the shape of the graph near the x-intercept. For simple roots, multiplicity 1 root, the graph passes directly through the x-axis, somewhat like a line. For even multiplicity roots, the graph touches the axis and turns around, so the axis is tangent to the graph at that point, and the point is both an x-intercept and a local extremum. For odd multiplicity roots of multiplicity greater than 1, so that would be 3, 5, 7, etc., the graph flattens out as it passes through the x-axis to the other side. It does go through the axis to the other side, but the point is both an x-intercept and an inflection point, and the graph has a horizontal tangent line, goes nearly flat as it goes through the point. They can have several extrema. The number of local extrema can go up to 1 less than the degree of the polynomial. The local extrema are evenly divided between max and minima, as even as possible. There's an odd number of them. Obviously, you have one more than one than you do the other. Each even degree polynomial function has a global extremum. If the leading coefficient is negative, then the arrows point down on both ends, and so the range is from negative infinity up to and including the y-coordinate of the maximum. And if the leading coefficient is positive, the arrows point up on the right and the left, and the range is the closed interval from the y-coordinate of the minimum up to positive infinity. Each odd degree polynomial does not have a global extremum. Its range is all real numbers. But of course it could have possibly several local extrema. The number of inflection points can go up to 2 less than the degree of the polynomial. The end behavior, or the basic shape of the graph on the extreme right and extreme left, is completely determined by the leading term, and the end behavior is exactly like that of power function defined by the leading term of the polynomial function. Even though they may go up and down for a while, in the end it settles down to look like a power function. So I'm going to stop there, and then we'll come back for one more video to wrap things up after this.